From the Gedanken Institute, walking you through a problem. It's a challenging problem. The problem is you roll 6 dice. What's the probability that 4 of the 6 possible numbers appear? This looks like a probability problem. Indeed, it is a probability problem, but this is not a lesson in probability. This is a lesson in problem solving, a lesson in how to tackle challenging problems. The only knowledge that you need to solve the problem is the fact that the probability of a die landing on any one of the 6 numbers is 1/6. There's no number that's preferred. Each of the 6 numbers is equally likely. This is true no matter how many dice you have. Each die is independent. You might think that you need to understand combinations, permutations, factorials, rules of probability, mutually exclusive, conditional probabilities, all of this technical jargon, and we think you don't. You need to understand that when you roll 1 die, the probability of it landing on any number is 1/6, and you have to be able to problem solve. You have to be able to figure things out. You have to be able to think for yourself. So what now? There's 2 basic responses when somebody gets a hard problem. They're sheep-like and wolf-like. A sheep would say something like, I didn't have probability in school. I hate probability. Isn't there some formula for this? And of course, the sheep would get help. I don't know what to do. Please tell me what to do. Do an internet search. Maybe I can Google the answer. Wolves have standard response. Sit and think hard. They problem solve. A wolf gets a challenging problem and the wolf says, I have no idea how to solve this problem. What a great opportunity to learn. The sheep says, I don't know how to do this problem, and they're completely stuck. They can't move forward. Wolves figured out a way to move forward. The best way to move forward is to try to understand what's going on. So what's an example? What does it mean? 4 of 6 possible numbers. What does that even mean? Let's think about it. What about this roll? 4, 4, 2, 5, 2, 1. 6 dice. Those are how many different numbers we got? We got the 1, we got the 2, we got the 4, we got the 5. We're missing the 3 and the 6. That is 4 different numbers. 4 of the 6 possible numbers appear. 2 don't appear. What's the probability of getting 4 of 6 numbers? Let's just guess. Is it 50%? Is it 75%? Is it 20%? Which do you think is most likely? Is 5 different numbers more likely than 4? What about 3 different numbers? An example of 3 different numbers would be, for example, 2, 2, 4, 4, 4, 6. That's 3 different numbers. It seems like 4's got to be more likely than 3, and maybe more likely than 5 as well. 6, that means 1 of each number. That seems pretty rare. Well, the reason why this problem is interesting, besides it being hard, is that there was a gambler in the 1700s, and he knew from experience, from rolling 6 dice a lot, that the probability of getting exactly 4 different numbers was very close to 50%. It happened about half the time, and he wanted to know whether it was more than 50% so he could bet on it happening, or if it was lower than 50%, he would bet against it happening. This is a hard problem. The standard strategy you get when you get a problem that you don't know how to do, you just don't do it. And I'm being serious, it's too hard. Don't try to move forward with this problem. Instead of trying to get some equation and plug some numbers in, we have to go backwards. Wolves go backwards. Wolves don't go forward unless they understand exactly what's going on. It has to make sense. They have to understand the concepts fundamentally. So we're going to start trying to understand probability from the very beginning. We're going to go all the way back. We're going to flip a coin. 50% chance it's heads, 50% chance it's tails. Got this? You think you got this? If you flip a head 3 times in a row, when you have a fair coin, what's the probability of heads on the next flip? Yeah, it's 50%. That's the definition of flipping a coin. It's 50% every time, no matter what. We flip a coin, it's 50% heads, 50% tails. Now let's flip 2 coins. Possible number of heads are 0, but they're both tails, 1 head when there's a head and a tail, and 2 heads when they're both heads. So what's the probability that there's one heads and one tail? So you flip two coins a lot, and you put down tally marks. About how many of the time will you get one head and one tail? Well, D'Alembert, in the 1700s, author of several works on probability, claimed that when two coins are tossed, the probability of one head and one tail is 1/3, because the number of heads that would turn up is 0, 1, or 2, and you should assign equal probability to these three outcomes. And this is wrong. This is wrong. Humans were measuring the speed of light before we understood that when you flip two coins, the probability of one head and one tail is 50%. This is a very challenging concept to fundamentally understand. It's easy to know it if somebody tells it to you, but to fundamentally understand it is challenging. Somebody can tell you it's 50% because the combination of tails and heads has two permutations, and you can nod your head and say, okay, I believe you, but that's not good enough. You can't just know, you have to understand. Raise your standards. Let's examine two coins, and let's make the coins different. A quarter and a penny. If we flip a quarter and a penny, the only way there can be two heads is if the quarter is heads and the penny is heads. But for heads and a tail, the quarter can be heads, the penny can be tails, or vice versa. There's two different ways to do it. It's very hard to see that there are two different ways when you're flipping two pennies. But if you're flipping a quarter and a penny, then it makes it easier to see. And that's what we're trying to do. We're trying to see it. What about if you flip the coins one at a time? And you pick two heads. You think it's going to be two heads. And I say, I think it's going to be one of each. And we flip the coins one at a time. What are you hoping for in the first flip? You're hoping for one thing. It's got to be heads, or else you're out. Me, I don't care. I don't care what the first coin is. It could be heads or tails. The only thing that I care about is the second coin. The second coin can't match the first coin, and that's 50%. So we're trying to wrap our head around, get this understanding that when you flip two coins, the probability is of one head and one tails is 50%. Flip them one at a time. Here's the summary of the results for the quarter penny. They could be heads and heads. The quarter can be heads, the penny can be tails. The quarter can be tails, the penny can be heads. The quarter can be tails, the penny can be tails. There's four possible outcomes. In two of those outcomes, there's one tail and one head. You can do them one at a time. It's the same thing. First coin flipped can be heads, second coin can be heads. The probability of that is 25%. The first coin being heads is second coin being tails is also 25%. First coin being tails, second coin being heads, 25%. Both tails, 25%. Each is 25%. In two of those, there's one head and one tail. So now you can see that two out of the four possible outcomes have one head and one tail, making the probability 2 out of 4, which is 50%. You may think you understand this. Perhaps you do. Let's see if you do. And that's the subject of video 2. Thanks for watching.